Yeah, there's probably a lot of things I shouldn't do, but it's all right. Today we're going to talk about center of mass and statics. Now, before I put the equation up there, but it's not going to mean anything to you because you don't have enough tools behind it. And a lot of times when I talk to students about center of mass, they are confused about what the equation actually means. So let's put the meter stick up here because we know the center of mass of meter stick is in its middle. So it's a good reference point. The first thing you should write in your notes is that center of mass is a location. It's a place. So when we say center of mass, we are talking about something measured in centimeters or meters or feet or something like that. In one dimension, it would be a single distance. In two dimensions, it would be two distances, and so on. So it is a location. So first, when we ask where is the center of mass, we need a point of reference to make that measurement. So like anything else, you have to pick some place that you're going to reference all of your measurements from. So I'm going to say the edge of the meter stick. Let's make that our point of reference. We'll start at 0. We'll say that that's where our measurements are going to be made from. To find center of mass, which is a location, we have to break our object up into little pieces because each piece contributes differently to the center of mass. We take and break our object up into individual pieces of mass m, and we multiply by their distance from your reference point to where that piece is located. And we start with the first piece and end with the last piece. The last piece would be whatever number of pieces you break it up into. We then divide by the total mass. Now, we can't actually physically break the meter stick up into pieces and measure it. And because you guys are eventually very likely to go into a higher level of math than you're in now, you should note that in the future, the actual way that you do this involves calculus. We are doing a simplification of what calculus could do for this problem. So we did this in mechanics. Not much, but we did it in mechanics. We also did this in mechanics, and that's what your guys are going to be capable of doing. So let me show you an example of how this would be done. We're going to take the meter stick and we're going to break it up into individual little pieces. I think 10 pieces is probably enough to drive the point home, but the more pieces you use, the more accurate this will be. This is a meter stick. We're going to get the right answer. It's pretty simple. But if you have a more complicated shape, breaking it into more pieces is better. That okay so far? So let's start by breaking it into 10 pieces. So I'm going to break it into 10 pieces, but if you're drawing yours, good luck. I think that looks pretty good. I broke mine into 10 pieces. Did you break yours into 10 pieces? What is the mass of one piece? Well, how about I say it different? If the total mass is m, what is the mass of one piece? 1/10 m. So each piece has a mass of 1/10 m. Now we're going to use the center of each piece as the location of each piece. So where's the center of the first piece? Sure. What's the length of the piece? It's a meter stick. Yeah, it's a meter stick. So each piece is 10 centimeters long. The middle of a 10 centimeter long piece would be 5 centimeters. Where's the location of the second piece's middle? And the next one's middle? All right, so we have an idea of where all the centers are. All right, let's show you how this works. A summation is exactly that. You are summing. So we're gonna dissect the summation. Piece number 1, its mass is 1/10 m. And x represents the location from my point of reference to where the first piece is, which is 5 centimeters. What's the mass of the second piece? 1/10 m. What's the location to the center of the second piece? Where? If I'm looking at this distance, I start at the reference for this one, so it's not at 5. Where is it? It's not at 10. 15. Do I need to explain why it's 15 and not 10 or 5? Okay. Now there's 10 total pieces, so I'm getting concerning feedback here. So let's do the third piece before I let you do the rest. Third piece's mass is 1/10 m. Where is the third piece? 25. Good job. Are you seeing a trend? Is a pattern developing? Do you notice that each piece has 1/10 m in it? So I think we could probably factor out the 1/10 m. Inside here, I just have the locations to each piece. And it starts 5, then it's 15, then it's 25. What do you think the next one is? You guys have heard of recursive formulas before, right? This is a recursive formula. You study them because they're a precursor to calculus. This is going to go all the way to piece number 10, which is located where? 95, that's right. All divided by m. Whoever's playing, stop, please. You moved everything around now, whoever you are. So stop touching your screen or I'll just go shut you down and not play anymore. Do you understand? Because you're not fessing up either. So finish it, please. Do the work. And you guys who touch the screen, you have to write the answer on the screen since you're so interested. But you're probably a coward, so you won't. So the top gives you 1/10 m times 500. And the bottom is still m. The bottom was the mass of the whole thing. We factored out 1/10 m from each term. And when you add 5 plus 15 plus 25 all the way to 95, you get 500. It shouldn't be a surprise. M's cancel because this has got to be a location. 1/10 of 500 is 50. Of course it is. The center of mass of a meter stick is at its middle, 50 centimeters. We knew the answer before we started. My goal had just been to show you how to get there. It's hard to see that now because everything got screwed up for the person who just had to move the screen. But remember, work on what I actually wanted to do today, which was to talk about the bridge problem. We dealt with center of mass just now, but I really want to talk to you about statics. Has anybody driven over the Howard Franklin Bridge? I am forever impressed with the construction of the new span of the bridge. What you guys may or may not know is that the old span is going to be knocked down. The old span was here when I left Florida in '86. And when I came back in 2004, the new span was in place. There was a time when just the old span was the only bridge that was 275. So it was 2 lanes in each direction. If you've ever been stuck in traffic on the Howard Franklin, understand that it's now 4 lanes in both directions, and it still gets completely backed up. When the new bridge goes online, it'll be 4 lanes in one direction, and then 4 lanes in the other, and then 2 lanes that are going to be HOV lanes on the new span, and a dedicated bicycle footpath on the new lanes too. It's huge. And building a new bridge isn't just about the bridge itself. They now have to take all the streets that lead into it, all those on-ramps and off-ramps on both sides, all have to be shifted over now because they're going to knock out the old bridge. And so those roads have to be moved over to the new span. What is considered the middle span now is going to be the traffic going north on 275. And all the new spans are going to be the traffic going south on 275. Bridges are rated for a number of years. This is supposed to be a 100-year bridge. The new spans, the middle spans now, those were an 80-year bridge. And the old bridge was also an 80-year bridge, and it's reaching the end of its life. So the company that's going to tear it down, probably going to turn it into some fishing piers on either side. That's what they did with the old Skyway Bridge. You guys weren't alive for what happened to the Skyway to understand why we have a Skyway Bridge now. The old Skyway was destroyed in an accident. A boat hit it, I think in 1983 or 85, somewhere in there, during morning rush hour during a fog. It was a horrible accident. People driving to it, there's no phones or cell phones back then, but people driving to work just drove off the span. And many people died in the accident. They ended up knocking the bridge down and building the Skyway in its place. The old bridge wasn't a very high bridge. It had a single span in the middle that was not suspension. The new bridge is much higher, but it's still 20 feet too short. The 20 feet that they should have done to make the bridge higher has prevented us from being a major port. Tampa would have been a major port because we are closer to the canal than Mississippi and Louisiana, which are the major deep water ports now for most traffic coming in from the canal. Tampa would have been a major cruise port and a major destination port for deep water craft. Things like those huge container ships, they can't get under that bridge. It needed 20 extra feet. Now, some would argue that that has protected the bay, and maybe that's probably a good thing. But some have argued that we've lost an incredible amount of opportunity economically. I'm not here for either of those. The truth is, I find the Skyway to be an amazing feat of engineering. And I think the new spans, just watching them be built, is an amazing feat of engineering. I know that you guys are young, but you take for granted that things just get built. If you've been driving the span at all, every time you drive it, maybe every month, you'll notice huge changes to the bridge as they bring in the massive segments that are the original foundations and then concrete over the top of them. They have to also put all those pylons, down to the ocean floor, the bay floor. And there's no bedrock, but they try to get as deep as I don't know what the qualities are. I know they pound the stakes into the ground until they reach a certain amount of force necessary to stay there. You'll notice that when there's the big spikes coming out of the ground, they have little red lines drawn like every foot. That's so they know how far it's been driven into the ground. And they drive them until a certain amount of force won't drive them downwards anymore. Then they cut them off and put the new spans on that. And that's how they've been working as they keep going. Those big platforms, you generally don't see them moving around much because they have 4 spikes on each corner. They have to lift those spikes up, move the platform using tugboats generally, and then drive those spikes back into the ground so that the cranes have leverage to be able to build the bridge. It's an amazing undertaking. And again, all with that caustic seawater lapping at it the whole time. And it's supposed to last for 100 years. This is a little personal to me because I don't know if you're aware of it, but the bridge I've been driving over every day on the trail recently got condemned and shut down. apparently they were able to put their hand through the wooden supports that were underneath it. It's just a wooden bridge. Further up the trail is a suspension bridge that's also pretty old. And that one goes over the same Rocky Creek Canal that loops its way through where the trail is. They were already planning on rebuilding the bridge, but now the trail will be shut down for 2 years because the bridge has been condemned and they're going to knock it down early. So, I mean, this is our infrastructure. This is your community. These are the kinds of projects that are taking place all the time. We're going to study simple bridge projects or simple bridge problems because they're kind of neat and they're interesting and they're a simple place to start. So what I've constructed for you is a simple suspension bridge. It's being suspended by 2 major cables. And I know it's just a meter stick, but this is where a bridge problem starts. This bridge problem has 2 cables, one located at the 20 centimeter mark and one located at the 80 centimeter mark. That's where we had it start. And I'll get this back up on the screen. Even right now, it's showing 0.39 and 0.37 as the forces pulling upwards on those cables, which tells me that the weight of the bridge has got to be the sum of 0.39 plus 0.37. It has to be mg for the bridge. So right now I have it set symmetrically, and I'm doing that on purpose because symmetrical works out well. But I want you to think, if we didn't know the mass of the bridge, this situation would be able to tell us the mass of the bridge because we can add up the 2 force probes and from there determine what the downward force is. But what if I want to take and say, shift this to the side and just put it down? If I don't have the force probes on, is there any way to predict what the 2 forces will be? I want you to think about, let's say we reverse the situation, meaning say that I don't know the 2 tensions. I mean, I know I have probes going on right now, but if you're trying to design a bridge, you can't build it and then decide what the forces will be later. So let's say I don't know what that is. And I want to shift where the supports are and predict what the 2 tensions will be. I know that this will be the tension on the left, and this will be the tension on the right. Sorry to bore you. And this will be the weight downwards, which is about 0.8 newtons. It's a little less than that, but we'll just use 0.8 for now. Net force can only tell me so much here. I know the net force on the system is 0 because the system isn't accelerating. So if I were to kind of write out the force equation, I have 2 upward forces and 1 downward force. Without more information, there's really no way for me to know what the 2 tensions would be. It's just not enough. Statics problems, when we did them first semester, we never worried about where the forces were applied. We did static problems that didn't have that as part of the problem. But now we're more sophisticated. We understand that where a force is applied also contributes to something called torque. In a static problem, both net force and net torque are both equal to 0. So what we're going to do is we're going to try a static problem. And I want to show you how a static problem is done. We're going to do this twice. We're going to do the offset problem, like I set up here. We're going to pick some places to put the force probes. And we're going to try and predict what the tensions are. And then we're going to do a load program where we're going to set the bridge back up to be symmetrical. We're going to place a load somewhere on the bridge and predict what the tensions should be. Everybody follow along? All right. So let's start by choosing where I want our supports to be. This one's currently at, put it right at 10. I think that way, but see how it's kind of at an angle? So I want to kind of shift this around. So put this at 70. But I want to make sure that the strings are perpendicular. So do they look perpendicular, you guys? That way the forces are pulling straight up. So all right. We know the meter stick's mass acts at its center. That's at 50. And we've placed one of these forces at 10 and one of these forces at 70. Okay, so 10, 50, 70. There are some extra steps that we have to go through to do torque problems because torque is a little more complicated than force. I'll remind you that to calculate a torque, you need to know three things. You need the size of the force or a placeholder. You need the distance from the pivot point to where that force is applied, and you need the angle at which that force acts. Those are the three things that you need. We have three forces acting on our meter stick. Before we could talk about torque, we have to choose a pivot point. This is different than what we had to do last time. We didn't have to choose a fulcrum when we dealt with force, but with a torque problem, we have to choose a pivot point, a point that the system pivots about. There's options. Sometimes it's given to you. So they could just give you one that you must use. In static problems, you can choose anywhere. Because the system is not actually rotating, there is no actual pivot. You may choose anywhere. If it is a static problem, I would encourage you to choose a place that eliminates a force. If I were you, I would choose a place that eliminates a force. So based on this set of rules, we can pick anywhere in the meter stick for our fulcrum. But I have two unknowns. If I can eliminate one of the unknowns, I think I should do it. So I'm going to choose to place the fulcrum here so that my torques will be measured from the 10 centimeter mark. By placing it here, I'm saying that TR doesn't apply a torque to the system because my pivot point is at that force. So the torque arm for that force is 0. Everybody follow why I'm doing that? It eliminates one of the torques. Well, if you don't understand why I'm doing it, at least write down that I'm doing it so that we can work the problem. Next, like a force problem, you have to sum all the forces, taking into account their direction, and then set them equal to 0. In this, we have to sum all the torques, taking into account their direction, and set them equal to 0. It's the same idea, except that torque has multiple things that have to be taken into account. Based on where my fulcrum is, there are two separate torques. There will be a torque for each force that's not at the fulcrum. So I'll have a torque from the meter stick and a torque from T left. Although I think my picture on the board is reversed from what we have in class. If you want, I can shift it over. We're okay, aren't we? All right. So with each torque, we have to list the length of the torque arm, the size of the force, and sine of the angle. I've tried to make all the angles 90 degrees, but we still have to go through and do the torque arms. So this is our first force, the meter stick. What is this length? 40. So I'm going to actually use meters and kilograms. So that's 0.4 meters. The size of this force, 0.8. It's actually a little less than that, but I'll put 0.8 newtons because that's the weight of the meter stick. And then sine 90 degrees. Can you guys do the next one on your own, please? And I'll call on one of you. All the time we can muster for this because we're going to run out of time otherwise. So what is the distance from the pivot point to TL? 60 or 0.6 meters. We don't know the size of that force. That's why it's an unknown. And then we put in sine of 90 degrees because we're trying to make the angle not a thing in this example. Now, we have to take into account the direction. So do you want into the board to be positive or into the board to be negative? All right, so into the board is negative. I'm going to put it on the pivot point. Into the board is negative. So right hand rule. First torque arm, I point my finger towards the torque arm, and then I roll my wrist until my middle finger is pointed in the direction of the force. Thank you. It looks like the first one is out of the board. Right? It's trying to make the meter stick go that way. Okay. So that's positive. That's the next force. Torque arm is from the pivot point to the next force. Roll my finger around so my middle finger points in the direction of the force. And then my thumb into the board. That's negative. Now, look at the picture, guys. This is definitely the direction that one's making it go. And this is definitely the direction that one's making it go, right? You just do that and say one's positive and one's negative. The right-hand rule is something I want you to know, but you can reason out that one of these is trying to make it go in one direction and one of these is trying to make it go in another direction. David? I don't know. That's why we're trying to figure this out. I don't think so. I would hope the TL is holding less than the higher weight of the bridge. Right? I don't think TR is 0. We eliminated it from the torque equation. That doesn't mean it's 0. R is 0 for that torque, but TL isn't 0. I'm sorry, TR isn't 0. All right. 0.4 times 0.8. 0.32. And that's 0.6 times TL. This has a sum to be equal to 0. Just adding up all the torques setting it equal to 0. You guys have calculators. Do the math there for me. What's TL? It's 0.32 divided by 0.6. 0.53. All right. Newtons. Right here, we can figure out TR by going back to our force equation. So do that, please. Tell me what TR is. At the sum to be equal to 0.8. So what do you get, 0.27? Right? Now, I mean, it had to work out that way, right? I mean, a little variance, sure, but not bad, right? All right. Go away. Have a nice day.